Today, our symposium covers all the exciting new areas that in the recent years has made tremendous progress. So our next session will cover another area that's leading to exciting new discoveries and potentially very long-lasting consequence to our society, which is the quantum information and quantum computing. I forgot to introduce. I'm Liang Jiang, theoretical physics at Stanford University. I'm the chair of the next two sessions. And it's my pleasure to introduce our keynote speaker, Professor Liang Jiang, from the Pritzker School of Molecular Engineering at the University of Chicago. Since 2020, he has also been an Amazon scholar working with the Amazon Web Services Center for Quantum Computing. Professor Jiang is a theorist in quantum information science whose work addresses one of the central challenges in quantum technology, which is preserving the fragile quantum information long enough for reliable and useful quantum devices. His group develops quantum control and error correction methods to protect quantum states from decoherence with applications across quantum computing, communication, sensing, simulation, and transduction. His work has helped shape ideas for modular quantum computation, global scale quantum networks, quantum sensing, and ways to connect different quantum platforms. Professor Jiang received the American Physics Society's Rolf Lander and Charles Binet Award in quantum computing. He was elected a fellow of American Physics Society in 2021 and received both the Alfred Sloan Research Fellowship and the Packard Fellowship for Science and Engineering. Let's welcome Professor Liang Jiang.
Okay, well, thank you for the introduction, Liang. And today I'm going to talk about quantum computing. So first, what is quantum computing? Quantum computing using quantum mechanics laws to process information. And so before we talk about quantum computing, maybe we can first look at, okay, how we process information like more than 80 years ago. And this is actually what you see on the screen is the first programmable computer, which is called the Colossus, which was built during the Second World War. And the British actually built this computer to break the code. And actually, the concept here is actually really you can use classical mechanics to actually process the information to help you to achieve a computational task. So now, during the past 80 years, we actually significantly advances our capability of doing classical computing. So nowadays, we have an iPhone, which can hold in hands, which is a super powerful computer compared to even the previous computer we had early on. And we can even have computing clusters can do computation in parallel. But although these computers look very different, they actually have something in common, which is a model of doing computation, that they're actually using classical bits to store information and using classical gates to process information. So we're actually being really, really good at this. And we're already making significant advances, including the recent developments of AI. So now one question is there any limits about what we can do with the classical computing? Or are there questions which is actually we still find it very difficult to solve with our classical computing? And if we look at further, indeed, there are questions which might be of interest to audience from different backgrounds. For example, the high TC superconductivity. It would be great if we could have room temperature superconductors. However, we explored for decades and we still haven't found it. And how to understand different high TC is actually an outstanding open question, which we spend a lot of classical computing power on it. We still haven't been able to fully solve the question. The other is nitrogen fixation. We have this nitrogenesis protein, which can actually convert nitrogen to ammonia, which is a very important biological process. But for this protein, which is actually consists of many atoms and molecules, we actually still don't know how it functions. So for these systems, there's one thing in common, which is the underlying electron and nucleus, they are quantum mechanical. And we know for quantum mechanical systems, actually when we increase the size of the quantum mechanical system, the resource we need for a classical computer to describe it will grow exponentially. Okay, so currently our classical computer can probably describe a few dozen quantum bits, and if a system beyond that, we're running out of classical memory to describe it. So on one hand, there's a linear increase of a quantum system, while a classical computer will need an exponential increase of memory to process or to store and process such information. So this mismatch is actually fundamental. It's because we are using our classical language to describe which is something which is fundamentally quantum mechanical. And it is this mismatch which leads to the limitation of our use of a classical computer to solve these quantum mechanical type of problems. Okay, so how to address this question? Okay, how to address such a open challenge? And actually, if we trace back, in 1982, Richard Feynman had already proposed the idea of using machines that based on the laws of quantum mechanics instead of laws of classical physics to solve these problems. Right? It makes more sense to use our quantum mechanical machine to solve a quantum mechanical problem. Then we will not encounter this mismatch of the resource overhead to do the computation. Okay, so one may ask, what's so magic about quantum? And here, it's just a simple slide, give you the two key ingredients of the key distinct features of quantum information processing. The first ingredient is superposition. In classical computation, we use classical bits, which will take value either 0 or 1. In quantum computing, we actually use the quantum bits called the qubits, which can be a superposition of 0 and 1, which can continuously vary from 0 to 1 with different amplitude and different relative phase. So it's because of this continuous variation, we actually can use it to build quantum sensors, which can give us sensitivity which cannot be achieved with our classical sensors. Okay. And for computing, actually this superposition is also important. Because if you have, say, 100 bits, you can only store 100 outcomes, but actually 100 bits. But if you have 100 qubits, you can sort of simultaneously have a superposition with 2 to the 100 different possibilities that cannot be stored in this quantum state. However, just have this simultaneous superposition is not enough. We also need to be able to extract the information because we still live in the classical world. So we require to use clever designed quantum algorithms to interfere these superpositions so that finally our classical readout will give us a sensible outcome. So that is actually the non-trivialness of designing quantum algorithm to take advantage of the superposition and the parallelism. And the other key concept is called entanglement. And entanglement is actually, you can think of the joint quantum states over two quantum systems. And it actually can give you extremely strong correlations which actually do not have a correspondence in the classical world. And more importantly, when the two quantum bits are maximally entangled, there is a guarantee that it has no correlation with the rest of the universe. And this monogamy of entanglement is actually crucial because it sets the foundations for secure quantum communication. Because if the two qubits are maximally entangled, then guarantee that nobody else knows what the outcome will be. So therefore, this guarantees the security for communication. So with these unique properties of quantum, actually, what can we build a quantum system that can have these features? And actually, during the past decades of the fundamental research, actually, we have made significant advances in building various types of quantum platforms, including superconducting circuits, trapped ions, neutral atoms, photons, phonons, and there are many other quantum platforms. And you can see that based on our understanding of superconductivity, Josephson effects, which is the key ingredient of building superconducting qubits, and also the last year's Nobel Prize of macroscopic tunneling, which also help us to understand and build such macroscopic quantum systems. And we have developed the Paul trap and a good control over ions, so that we have exquisite quantum gates to do it. And for neutral atoms, we have laser cooling, Bose-Einstein condensation, and also optical tweezers to move atoms around, and as well as ultra-high precision spectroscopy, as well as entanglement being demonstrated experimentally. So these different platforms, they actually they are not a competing thrust. You can think of them as a resource from different engineering capabilities. For example, the superconducting qubits can be really fast in processing quantum gates. The ions can have a very precise controls and long memories. And the atoms, you can have a tweezer to move them around with a good connectivity to do coupling gates. And the photons is a natural media that you can send information over long distance through fibers of space communications. So therefore, like these, instead of just a competing thrust, if you combine them together, you might be able to have a joint combined quantum system with capability that will open up new possibilities. Okay, so now with these platforms, what can we do with quantum, right? So we need to develop some quantum algorithms to use these platforms to do something non-trivial. And here I'm going to point out like one quantum algorithm, which is Shor's factoring algorithm. So we probably know like if you give a large number, it's actually very difficult to find its factors. And this is actually the foundation of crypto systems. Okay, however, Peter Shor in 1994 found that actually if you could have a quantum computer, we can actually efficiently factorize large numbers. So here I'm trying to give you like a flavor of what are the key ingredients of Shor's algorithm. So the workhorse is actually called the quantum Fourier transform. So it actually can give you exponential speed up to do a Fourier transform, which is important to find the periodicity of a function. And then with this finding the period of certain functions, combined with the classical number theory, we will be able to efficiently find the prime factors of the big numbers. Okay, so then if we have the capability to do the factoring, then actually our current RSA encryption system will be compromised. For example, you have a large number, which is the public key, but the secret information is actually associated with those two prime compositions. But if you have a quantum computer, you'll get that, then that allows you to extract the private key. And besides the RSA, there are other crypto systems, including Diffie-Hellman, elliptic curve. All these crypto schemes will be compromised because they're building on assumption of a complexity for calculating mathematical problems, but actually quantum computer can solve those problems efficiently. So with that said, later I will also talk about actually quantum communication allows you to actually give you a new communication system, which actually will give you security, which classically you cannot. Okay, but let's get back to the quantum computing. So now we have a really good, solid quantum algorithm that can efficiently factor in large numbers. Can we build a device to actually factor it? Well, it was proposed in 1994, and more than 30 years has passed, and we're actually making progress towards building a large quantum computer that can factor large numbers. So like maybe right after Shor's algorithm, people develop like efficient, robust control protocols to do quantum gates over a qubit or multiple qubits. And then people go to intermediate scale with about like 100 qubits so that you can verify that there is something quantum in there that classically cannot simulate. But as we build the larger systems, we find that actually the system becomes very noisy because the quantum information is actually very fragile. And once you build a larger system, actually it's become difficult to harness the quantumness in the presence of noise. That's why actually we need this quantum error correction to encode the information at a logical level so that to protect the quantumness from the noisy environment, which has been demonstrated using atoms, ions, and superconductors. And until like recently, that was about 2 years ago, then Google did this demonstrate that you can actually build a fault-tolerant quantum system so that you can actually process information using these noisy quantum devices. But so far, we still have a very limited size of a fault-tolerant system, so that the next challenge is actually to scale it up to build a large-scale fault-tolerant quantum system. So one may ask, why take about 30 years to even get to such a level? Isn't it just a few qubits or a few atoms and ions? The challenges actually come from the following. First, we have noise everywhere. Okay, it's unavoidable to have a noisy gates or measurements, and even the qubit is sitting there, it actually will dephase. So basically, you need to continuously fighting this noise to protect the information. And second is, it's actually very difficult to do quantum error correction, because unlike classical error correction, you can measure every classical bits and find out which bit is error. In quantum case, if you measure all the quantum bits, the protected quantum information is already collapsed. So you cannot measure individual quantum bits, so we have to develop collective syndrome measurement schemes to infer which qubit has error in order to do the error correction. So you can think that the quantum error correction is kind of like a refrigerator, which the noise are producing a lot of entropy, and you need to put the fresh ancilla in there to take the entropy away, but in a way that do not compromise the encoded information. And moreover, the ancillary you're putting in can also inject noise into the system. So you need to make sure that this whole process does not proliferate the error, so its error is under control while you're doing error correction. That is why it is non-trivial to do a fault-tolerant quantum error correction. Okay, so therefore, this whole effort of fault-tolerant error correction is not just to design error correcting codes. It's to build a whole system so that you can take care of the error with your noisy, imperfect quantum devices. Okay, so that's why it's actually important we need to co-design the quantum error correction. On one hand, we need to know the physical system, what's a noise, what's the connectivity of a device, and how good are these native controls we can do over the system. On the other hand, we want to know what's the application, what things you want to compute, or you want to use a quantum system for secure communication, or you want a quantum system to build a sensor. So for example, when you want to do error correction for sensing, you need to make sure error correction do not correct the noise signal you want to sense, but only correct the noise. And if you want to use error correction for communication, you probably want to make sure that actually you can communicate as much information as possible while doing error correction. And actually, we can also learn a lot from classical error correction while developing quantum error correction. And in classical error correction, it's actually widely used in our classical communication. So Shannon proposed the Shannon coding theorem, which gives the fundamental limits of how much information you can communicate over a noisy classical channel. And it took people half a century to basically get to the level developing polar code, LDPC code, which is currently used in our 5G networks. And if you carry the information using continuous variable degree of freedom, we'll also use the phase-shifted keying and the quadrature amplitude modulation, which is also used in Wi-Fi and Bluetooth. And in the quantum side, we also have some fundamental limits about how much information we can carry. And we're also developing different codes, which QLDPC code, which borrow kind of quantum version of the classical QLDPC code. And we also developed the Gottesman-Kitaev-Preskill code, which also can mimic what we do classically. So basically, this allows us to actually learn a lot from the classical to build efficient quantum codes. And here we talk about in terms of code design, is that when we design error correcting codes, we should know what is the error we should correct. Because error correction is not going to correct all errors. Otherwise, there will be no information being reserved. So we want to know what's the dominant error. For example, we know that an oscillator could be a quantum information carrier. The oscillator is kind of a physics abstraction in terms of you can encode information with the photon wave packets or superconducting cavities or motion of certain degrees of freedom. But these oscillators, we know they have many different energy eigenlevels. So it provides the redundancy to encode information. And the oscillator may suffer from this energy dissipation, and every time you lose the excitation, you reduce the energy level by 1. So for such a noise model, we actually plug into our optimization protocol. We actually find that it doesn't matter what initial coding you have, it will actually optimize towards a particular lattice pattern that you see on the right. And here, what I'm plotting is a Wigner distribution, which you can think as a quasi-probability distribution of the coding. So here you see that actually the hexagonal lattice might remind you of efficient packing. And later we find out that there is a deep connection between quantum error correction for these loss errors versus efficient packing in the phase space. And that actually guides us design to come up with, first this code was developed even more than 20 years ago, but the extension of these codes to higher dimension allows us to come up with the channel capacity achieving codes for quantum error correction for bosonic channels. And this is purely mathematical, but now actually people in the experiment also demonstrated that these bosonic error correction can actually be useful to extend the memory lifetime. So here we care about the dimensionless number, which is the ratio between the protected lifetime and the best component lifetime. If that ratio is larger than 1, which shows that the quantum error correction help you to extend the memory lifetime. And that was actually demonstrated 3 years ago, that actually we can extend the lifetime by at least a factor of 2. And this now the frontier for the bosonic error correction is now shifted from just demonstrating the memory. We should also demonstrate quantum gates with these multiple cavities so that we can efficiently correct errors while doing computation. And there are also other physical platforms. Besides oscillators, we also have spins or other finite energy level systems. And for these systems, we also need to co-design error correcting codes. So we know like in the superconductors, usually they have a substrate and you have a two-dimensional like layout of a superconductor. So therefore, given such a connectivity, we need to co-design the surface code, or if you have a capability to do bilayers, then you will be able to do bivariant bicycle codes. On the other hand, for atom systems, you have tweezers, you can move things around. Then in this case, actually, you will no longer be constrained by locality. Then you can design these quantum LDPC codes that have the efficient coding rate, which can be hardware efficient. So with these code designs, like different groups that develop their own codes and demonstrate some of them in the experiments. For example, this recent Google experiment that I mentioned earlier, using the surface code to show that as you increase the size of the code, the errors become smaller and smaller. And that's an exponential decrease of the error as you grow the system size. And that shows that, okay, maybe if we build the system better and better, then the errors will become sufficiently small so that we'll be able to perform a large-scale quantum computing like the Shor algorithm that we mentioned earlier. On the atomic platforms, we can also, because we can move things around, we can do this like QLDPC code. And so far, this is the proposal that we estimate we can have order of magnitude reduction in terms of the resources that we will need. So now, once we have the code, the architecture, then we can actually use that to estimate how much resource we really need to do a useful quantum computation. And earlier I mentioned the Shor factoring, there's the RSA encryption system, and there is this also another elliptic curve encryption, which is similar to the RSA. And here, based on the estimates with the state-of-art superconductor like surface code, we estimate probably we need 500,000 physical qubits, which run about 20 minutes to solve this elliptic curve crypto scheme. On the other hand, if you use atomic systems, because the clock cycle is a bit slower, but we need maybe a smaller number because of the connectivity is better, so we only need about like tens of thousands of qubits to solve these problems in a few days. And this elliptic curve crypto is actually used in the cryptocurrencies, so that's actually a practically relevant question. Okay, so therefore, this shows that actually co-design fault tolerance will allow us to create a real impact. And also, this is probably not too far away because we can already build thousands of physical qubits in superconductors. And in atom array systems, people also already trapped thousands of atoms. So it's just maybe one or two order of magnitude, we already will be able to get there. So therefore, actually, the co-designed quantum system is already bringing it closer to build a real quantum system that will have a real impact. On the other hand, I should also point out, okay, the quantum algorithm not just to do the code cracking, it also has other applications, right? You can also use that to simulate quantum systems or to do Grover search. So there are different applications of quantum algorithm. But here, I'm mostly focusing on this particular application. And besides computation, quantum could have also other applications. For example, we can use quantum to build different kinds of sensors. The sensor can be very small as like a yellow fluorescent protein. You can also have like spins in there that can sense the local magnetic field. And this will be important because later on you can use these fluorescent protein not just to signaling, it can also probe local magnetic field. And we know we can do NMR, but usually it's macroscopic. But now, potentially with that, you can do single molecule nuclear magnetic resonance. Which similarly, we also have like diamond defect centers, which relate to the material. And the defects in there will allow us to also like sense like signals, which is a kind of small quantum system. It turns out to also work at the room temperature. So it's compatible with biological applications. And we also have atomic clocks, which we know is very important because our GPS relies on the atomic clocks. But now the atomic clock can be so precise that even it can sense the gravitational shift if we move the clocks vertically. So this could also be useful for like geosensing. And another thing, which is also quantum, doesn't have to be small. It can be very big. And we can use this gravitational wave detector, which is like an interferometer that spans over like 4 kilometers for each arm, and to sense the gravitational wave. And the latest LIGO actually creates a quantum states so that you will go beyond a certain limit. You'll go beyond this standard limit so that you will be able to build more sensitivity sensors based on these gravitational wave sensors. And the other application is quantum communication. And the goal is actually to build like a global quantum network. And the challenge here is actually the optical loss when you try to communicate over long distances. The best media we have on Earth with the material is fiber, which send a photon over 20 kilometers. When beyond that, the success rate decreases exponentially. So to overcome this, one idea is to send a photon in outer space, which is vacuum. So that's why people use satellite-based communication to achieve a communication, quantum communication over thousands of kilometers. The other way is to still use a fiber, but you need a particular quantum device to kind of put every segment of fibers, but use quantum repeaters to relay and entangle signals. However, recently we come up with a different scheme, which is actually like a sort of integrating the previous two. Because the best medium to send photon is not material, it's actually vacuum. Because vacuum basically has no absorption, right? So if you can put the vacuum in the ground to create some vacuum enclosure, which is actually what people did in LIGO with 4-kilometer scale. Now here we're just saying, like maybe we can do something similar, but over thousands of kilometer scale. Every few kilometers, you can focus the beam with a lens, then you will be able to propagate photons. And we estimate the effective attenuation length could be thousands of kilometers, which means we can send a single photon across the continent. Moreover, for such a scheme for communication, we'll be able to achieve a channel capacity, which is every second you can send about 10 to the 13 qubits, which is 10 tera-qubits. So that's kind of the scale which we actually now have the fiber networks, which is that scale. But this time, it's sending quantum bits rather than classical bits. So maybe down the road, maybe the quantum entanglement may not be so precious because we can send so many qubits through. And maybe we'll have a cell phone package plan to send quantum bits rather than classical bits. Yeah. So now with these communication and sensings, we also can imagine that we can combine that with quantum computing devices. So for example, we can delegate blind computing so that we can send our computational task to the server to complete the task and send the message back to us without knowing what exactly the computation is. And we can also have distributed quantum computational sensing so that we can combine the quantum sensor, quantum network, and quantum computers together to build a quantum sensor. For example, there's some ideas that maybe this could be useful for dark matter search. Okay. So now let's kind of like take a look back. Okay, during the past 80 years, there have been significant development in classical computing so that we can go from this first programmable device to a really powerful device that we can hold in our hands. Okay, now here, as we gain more and more power to control the quantum system, we might envision that probably down the road, we might even have a different way to process the information. Rather than just process information with the classical bits, we might be able to process information with the quantum bits, which is actually what the nature does. And that will enable us to do and compute more. Thank you for your attention.